Hello, my name is Fabio Oliveira. In this tutorial, I will demonstrate how to generate images of handwritten digits using a deep convolutional generative adversarial network, DCGAN. The code is written using the Keras sequential API with a TF gradient tape training loop. But before, let's see some key concepts. Generative Adversarial Networks, GANs, are one of the most interesting ideas in computer science today. Two models are trained simultaneously by an adversarial process. A generator, the artist, learns to create images that look real, while a discriminator, the art critic, learns to tell real images apart from fakes. During training, the generator progressively becomes better and better at creating images that look real, while the discriminator becomes better at telling them apart. The process reaches equilibrium when the discriminator can no longer distinguish real images from fakes. The process reaches equilibrium when the discriminator can no longer distinguish real images from fakes. This tutorial demonstrates this process on the MINEST dataset, one of the most popular datasets in data science. The following animation shows a series of images produced by the generator, as it was trained for 50 epochs. The images begin as handle noise and increasingly resemble handwritten digits over time. We will use TensorFlow on the background coding using Colab. The resources used in this tutorial are, first, the library ImageU, which is a Python library that provides an easy interface to read and write a wide range of image data, including animated images, volumetric data, and scientific formats. We will use as well glob, which is another Python library that returns a list of files that match the given patterns, which is very important in this kind of network. We use matplotlib pyplot, which is a collection of functions that make matplotlib work like MATLAB. Each pyplot function makes some change to a figure. Therefore, we can create figures, plotting area in a figure, plot some lines in a plotting area, decorate the plot with labels, and generate GIFs animated as well. We use NumPy, of course, which is the fundamental package for scientific computing in Python. NumPy arrays facilitate advanced mathematical and other types of operations on large numbers of data. Typically, such operations are executed more efficiently and with less code than is possible using Python's built-in sequences. We use OS module in Python, which provides functions for interacting with the operating systems, meaning that TensorFlow will be interacting with the operating system that we will be using. We use the Python image library as well, which is a free and open source additional library for the Python programming language that adds support for opening, manipulating, and saving many different image file formats. We use Keras, which is the high-level API of TensorFlow 2, an approachable, high-productive interface for solving machine learning problems with a focus on modern deep learning. It provides essential abstractions and building blocks for developing and shipping machine learning solutions with high iteration velocity. We use the MINEST dataset, which is an acronym that stands for the Modified National Institute of Standards and Technology Dataset. It's a dataset of 60,000 small square 28 by 28 pixel grayscale images of handwritten single digits between 0 and 9. I will run this tutorial using Google Colab. Google Colab is a platform on the cloud from Google, as the name says, where you can run Python coding language using TensorFlow on the background to build deep neural networks such as the GAN that we will build now. It's very straightforward for using. You need to have a Google account. I am using my one. Once you connected, sign in with your Google account, you need to connect to the platform. I'm already connected. Typically, you have here a button for connecting to Colab using Python, Google Computing Engine, in the backend. What that means? Means that you are using GPUs, graphic processing units, which are more powerful computing power for running deep learning models. Okay, I open this notebook importing from TensorFlow. You go in TensorFlow and then you will see the address on the screen, and then you can go there and import this notebook as well for practicing in your time. We start importing TensorFlow for the background. This is the command line for importing TensorFlow. We will just check the last version, the version we are using, which is a 2.5, the last one. And now we will start installing and importing the libraries which I introduced to you before. So just click for running. Every time we click in this arrow, we are giving order to Python to run. As you can see, it's importing all the libraries and installing as well ImageAI. It's done. And now we will import the libraries. Done as well, very quick. We import all the libraries that I presented to you before. And now we will load the data set. Remember the -t data set, which we're gonna be using. And the generator will generate handwritten digits resembling the -t data set. Here we are going to run some commands for download the data, which is already on the TensorFlow library. We could import this data from our computer or from another website. The data is there already. Here we are just giving to TensorFlow and Python the definition about the type of image we are using, the data type we are using, and as well the size and the normalization of the image, because the image sometimes they have different sizes. We want to normalize this size. While we go through the code, I will explain some of the commands that we have here and some of the nomenclatures. We're not gonna go through every single line because it would be very time consuming. You can do that by your time, referring to the documentation, mainly documentation from TensorFlow and as well from Keras. So here the first that you can see, and I will explain, is float32. Float is a data type. A float variable can contain whole numbers and fractions. Float is a shortened term for floating point. By definition, it's a fundamental data type built into the compiler or the Python compiler that's used to define numeric values with floating decimal points. You can see as well here we have two other commands: buffer size 60,000 and batch size 256. What that means? Buffer size means that for perfect shuffling, we set the buffer size equal to the full size of the data set. For example, if your data set contains 10,000 elements, in our case which contains 60,000, but buffer size is set to 1,000, then Shuffle will initially select a random element from only the first 10,000 images, which is not what we want. We want them to select from all the data sets. And we have as well the batch size. Batch size is the number of training examples in one forward-backward pass. What that means? The neural networks, they go from the left to the right and to the right to the left in movements to learn and to check all the data sets. So the higher the batch size, the more memory space you need. Number of iterations as well, that which is the number of passes, each pass using batch size number of examples. Passes or epochs are the definition of how many times the model will see all the images of the data. Now we run and we will ask as well to the model to shuffle all the images randomly. Now we will create the models, both the generator and the discriminator, which will be defined using Keras Sequential API. In this block of commands, we are creating our neural network, which we call now generator. Okay? The generator will be the neural network that will learn the data and will build new digits based on the learning. Okay? So in the first, here we can see that we have a Python command defining a function, and this function will be regarding the construction of our deep neural network. We're gonna use here this block of text, this block of commands, and now I will explain intuitively what that means. We use the dense layer. In Keras, you can create layers to develop models. A model is usually a network of layers in which the most common type is a stack of layers. Adding a densely connected layer to the model will take an input array of 7 per 7 per 256. The shape of the data will be none, as you can see here, none, 7 per 7 per 256 after the first layer. In this case, you won't need to specify the size of the input moving forward because of automatic shape inference. We have the batch normalization command function similarly to preprocessing at every layer of the network. And we have the ReLU. ReLU, as we saw, is linear for all positive values and set to 0 for all negative values. LeakyReLU has a smaller slope for negative values instead of altogether 0. In this first layer, we have the generator using a transposed convolutional layer upsampling to produce an image from seed random noise. 128 is the dimensionality of the outspace. 128 is the dimensionality of the output space. 5. This two number 5 means it specifies the height and width of the 2D convolutional window. And we have strides 1 per 1. The second layer is pretty much the same, just changing the size for 14 and 64. And the last layer, the same thing, but now we have the output that will be 28 per 28 per 1, which means that we will see the digits in 28 per 28 pixels per 1 dimensionality because it's black and white. Another important concept to understand here, I mentioned sometimes the word or term seed, S-E-E-D. This term is an abbreviation of the standard term random seed. TensorFlow operators that produce random results accept an optional seed parameter. If you pass the same number to two instances of the same operator, they will produce the same sequence of results. Seed function is used to save the state of a random function so that it can generate same random numbers on multiple executions of the code on the same machine or on different machines for a specific seed value. The seed value is the previous value number generated by the generator. Now we will produce the generator. Now we are creating the generator. The generator uses TF-Keras layers, convolutional 2D transpose layers, to produce an image from a seed, random noise. We start with a dense layer that takes the seed as input, then upsample several times until we reach the desired image size of 28 per 28 per 1. Notice the TF-Keras layer as LeakyReLU activation for each layer except the output layer, which uses Tana. Here the model that is not trained yet has produced some image. Of course, doesn't mean anything because the model was not trained. The model didn't see any of the image that we provided to it yet. Here in this block of text, we will create a discriminator. It follows the same steps and with the same layers which we used in our previous model. We use the as yet untrained discriminator to classify the generated image as real or fake. The model will be trained to output positive values for real images and negative values for fake images. Now we'll define the laws and optimizers for both discriminator and generator. We define the laws, functions, and optimizers for both models. This method quantifies how well the discriminator is able to distinguish real images from fakes. It compares the discriminator's predictions on real images to an array of ones, and the discriminator's predictions on fake-generated image to an array of zeros. Now we will define the optimizers. Optimizer, the discriminator, and the generator optimizers are different since we will train two networks separately. The Adam optimization algorithm is an extension of stochastic gradient descent. Stochastic gradient descent maintains a single learning rate for all weight updates, while the learning rate does not change during training. A learning rate is maintained for each network weight and adapts as learning unfolds. The training loop begins with generator receiving a random. We define as well in this notebook how to save and restore models, which can be useful and helpful in case a long-running training task is interrupted, because you can come back to the training checkpoints and restart where it stopped. Now we define the training loop. The training loop begins with generator receiving a random seed as input. That seed is used to produce an image. The discriminator is then used to classify real images drawn from the training set and fakes images produced by the generator. The loss is calculated for each of these models, and the gradients are used to update the generator and discriminator. Here in this block of text we have two important concepts as well. The first one is epochs, as I said before, defines how many times the model will see all the data set. In this case will be 50. We add as well noise DIN. In its most basic form, a GAN takes random noise as its input. The generator then transforms this noise into a meaningful output. By introducing noise, we can get the GAN to produce a wide variety of data, sampling from different places in the target distribution. Now we will compile the model and start training the model. The model here will save the results as a checkpoint every 15 epochs and will display the output at the final of each epoch. Now we can generate and save images that the model will produce, and we will start training the model. At the beginning of the training, the generated images look like random noise. As training progresses, the generated digits will look increasingly real, and after about 50 epochs, they resemble ministry digits. This may take about 1 minute each epoch with the default settings on Colab. Now the model has finished training. We go for the restore listed checkpoint. And we create a GIF with the final work of the generator. We use this plotting using the pure image. We use ImageAI to create an animated GIF using the images saved during training that you just watched. This was the tutorial about the deep convolutional generative adversarial network using Colab and TensorFlow. I hope you enjoyed and learned with this work. Stay tuned for more. Bye bye!